I'm not sure why that was a thing. Anyway, so times W. Okay, what is this? That is weird. That's what it is. So if you think of these two instead of as vectors, but instead as like matrices, you're going to have v1, again, this thing right here, v1, no, not this. No, nope, I'm bad at drawing. v2 times, no, that's transposed, right? So it would be the v, which would be that. It's going to be like this. It's going to be a 2x1 matrix, or something like that. I'm not sure if I'm getting the order correctly, but honestly, it's been so long I've done any proper math. I've forgotten. So this is going to be what that is going to do. If you do just a regular dot product, it's going to be a vertical matrix first times a horizontal one, and that leads into a scalar C. But if we put this matrix in the middle, what we have, well, then we're going to have something different. Because if you think about it, here in the middle, you actually have the identity matrix, right? It's just sitting there. And that's what you usually have in the dot product. In the regular base, the identity matrix is the A here, and it's the middle thing. So, for example, if we had something different, if we had v1, v2, here we had, I'm sorry for the noise, I live next to a highway. If we have, instead of just 1, 0, we have 1, 0, minus 1 and 0. And then we have w1, w2. Oh god. Attacks again. There's a limit to my drawing tablet, and it follows suit here. This thing is going to be different to see. And well, what do we do here? We basically just changed the matrix in the middle. So what we did was that we defined a new bilinear form. Let's just call this one, instead of the dot product, let's call it B2, for example.
Hey, Duhan,
But I'm
before
gonna,
we get too far,
yep.
comment from the chat. It is supposed to be flipped. It's a row vector times a column vector to get you a scalar. Or
Yeah, I know. I'm just confused about this probably, but it's weird. I think it's because I've read Artin ages ago, and I don't exactly remember if they define vectors by default as being horizontal or vertical. I thought they were horizontal because that's usually how I write them, but I might be wrong about this. I'm terribly sorry. So probably the inverse of this thing right here. It's going to be like pen mode. This is going to be like let's just be lazy and do the transpose of these guys. It's going to be the inverse of this. It's going to be, here's going to be horizontal, and this one's going to be vertical. So yeah. Sorry about that. Okay. So let's begin with the next section, which is defining what exactly counts as a bilinear form. So here I did a very hand-wavy approach to it. I just told you, oh yeah, if you change the matrix in the middle, it's a bilinear form that is different from the one before. But what exactly counts as one? Well, I don't even think this, I'm not terribly sure if this one counts, but the definition of one is, I mean, the requirements to be a bilinear form is that it has to follow a couple things. First of all, I'm going to ditch this notation right here, and I'm going to start using the notation that the book uses for the rest of its strip around it, which is this. This is basically just, imagine these are parentheses and there's a b on the side. That's what it is. This is a bilinear form of v1 and v2. So v1 and v2, Am I doing this right? No, I'm doing this completely out of the blue. If we do v1 and v2, v1 plus v2, I mean, and that is a bilinear of w, what does this equal? This, by requirement of being a bilinear form, has to equal v1 w plus v2 w. That's a requirement of it being valid. Same kind of thing with w. So if we do v w1 w2 plus in the middle, this is going to equal v w1 plus v w2, right? This is a very important requirement. It's a algebraic thing that we're going to be using a lot to prove a lot of things, and it's just keep it in mind, really. So another thing that you have to keep in mind is that if you have a, scalar times one of these guys, so CV W, it's going to be equal to VCW, which by itself is equal to CVW. So you can basically do a bunch of linear-ish things with it. You can separate, decompose the sums in the inside of the bilinear forms, and you can get scalars out of the bilinear form to do whatever you want, really. Is the bracket notation being the same as an inner product intentional? I believe, yeah. I'm not terribly sure because, like, I think, like, I'm pretty sure Artin just kind of froze the notation in there, but he also does mention that the dot product is a bilinear form that also is an inner product or something like that. If you give me a little bit of time, I can check for you. Um, Our model for bilinear forms of dot product effects simple properties studied. Yeah, I'm not terribly sure of this, but like I think what that means. What means, Alex? What exactly you want me to give you later, of course, but still. Oh, yeah, like I guess we I guess he can do that, sure, if he wants, of course. But anyway, so these are the requirements. Continuing the class, this is going to be requirements for bilinear formulas going from here on out. There's a couple other things that you can do to classify them. Specifically, if you say that, are you hearing Stucky? Like I see your cursor in the corner, but still, whatever. If you have that V W is going to be equal to WV, that is not true all the time, and that means that this guy is oh god, it attacks again. I need to exit pen mode and go here. Then I need to go back. Symmetric. I think I wrote that correctly. So this guy is going to be symmetric. Exit pen mode. I go here. And that's not going to be true all the time. It's going to be very useful when it is. And I'm going to go touch on it later on. It leads into a concept that is called orthogonality. And it's very good for studying that. But then we have another type, which is called skew symmetry. We can do this, and this is going to be equal to minus WV. So that is skew symmetric. So this is as far as I've read, not terribly important, but it's a good thing to have. Just that if you invert, then you then have to give us a negative sign here. I am not horribly sure where this is used. I think I might have just skipped over it instead of properly studying it, but whatever. So let me go all the way back here because it's less crowded than the side. Let's start with some other things here. So we've touched on the definition of the bilinear forms in general, which is a vector transposed times a matrix, and that times another vector. That is going to be your general definition of it. But if A is symmetric, so is the bilinear form. And that's going to be a thing I'm going to prove for you right now. If anyone has any questions so far, it's best to ask them. Oh, here. When V is a real vector space, every inner product on V is bilinear for representation machine is definitely intentional. Oh yeah, that's fair enough. Thank you, Driss. I'm kind of new to this subject, so I mean, not really new. It's just been a while since I've read on it. Anyway, oh, that was an accident. So let's go with prop. What's it? The form 1.7 symmetric only if the matrix A is symmetric. Let me see what exactly I meant to this, because I have a note here that says look up 1.7 and I have no idea what that is. Oh, I found it. Okay. Oh god. New 1.7. I hope that I can just put this here. Yep, I just kind of have to scale it up. Can I? Pen mode, probably. Yeah, okay. Here we go. So this is 1.7, and we're going to have copy, paste, move here. This is the proposition. The form 1.7, which is this one, is symmetric if and only if the matrix A is symmetric. Okay, so I might have to paraphrase a little bit from the actual proof that Artin gives you, mostly to just keep from straying too far from the actual contents of the book. But let's go. I think I can just put this to the side. Can I can't pin it to the top. That's gonna be a bother, but okay. Assume that A is symmetric. So let's just assume for a second A is going to be a symmetric. Forgot the name. A symmetric matrix. Yeah. God, can't believe that. So that means that A, T, the transpose of A, is going to be equal to A. That's very important. For the following proof, then let me read it up because I'm confused about what I wrote here. I didn't believe that was going to be possible, but okay. Okay, so we're going to have a little bit of a talk here. Of course, if we have y, t, a, I think he wrote x. Yeah, x. X. This is going to be 1 by 1, right? So it's going to be just a single number c inside of matrix brackets as far as math is concerned. So what we do is that we're going to have that yt ax is going to be equal to its transpose, because the transpose of this guy is, of course, itself. We can clearly see this. Now we do yt ax t. That is going to be equal to y a. No, wait, I think I wrote this wrong. 1 second. I'm cooking wrong here. Yeah, you'll invert these. I'm stupid. Okay, it's going to be equal to x t a t y. And since this guy right here is symmetric, by our assumption, we're going to have that xt a y is going to be equal to yt ax. So if a is symmetric, we're going to have that the bilinear form is also going to be symmetric. Very good. Now, there's the other side of the implication, which is a little bit more complicated, but we can simply set x as being x line, which is what I'm going to call it, x minus ei. Ei is basically just going to be like, as far as I remember, it's going to be 0. No, it's a unit. I don't remember what it is. Oh, I think I see now. I think. What is ei again? 1 0. This guy's going to be 1 0, and ej, I think that's correct. It's going to be 0 1. I think that's right. It's probably mentioned somewhere up there, but I honestly just can't find it. Yeah, I can't find anything in this PDF. It's busted. But one potential and 0 elsewhere. Yeah, I found that to be like convincing to my brain at least. Like, okay, I'm probably going to be right on this. I just don't want to be wrong. So, okay, so x line is going to be equal to x, which we have before, minus ei, and then we are going to have y line is going to be equal to ej, which itself is going to be, wait, no, I think I deleted this on accident. It's going to be 0 1. Okay, all good here, right? Okay, no questions. So what we're going to do from here is that we're going to find that one second. EGI. Oh, I found it. Okay, I figured it out. So it's going to have that E I E J is going to be equal to text again. Not again. No. Damn it. It's going to be equal to E. No. Why am I? Okay. Sorry. EI transpose A EJ minus AIJ. I suppose that's what it's written here. I don't want to do the computation myself. That's why I'm checking. But yeah, that's right. While we have that EJ EI is going to be equal to AJI. That's correct. That is correct. All right. Everything good so far? I think so. All right. Now, if we have that the form is symmetric, then these guys are going to be equal, right? Somewhat. Let me wait. Not these guys specifically. We're gonna have that A I J is going to be equal to a J I, and so A is going to be symmetric because like, yeah, this is like, now that I think about it, this thing is probably a little bit inaccurate. This is not exactly what the definition of I is, but this is of EI, and this is not the definition of EJ. It's exactly as like Driz said, that this is going to be 0 elsewhere and 1 exactly in the ith index. I think that's how you say it. In the index of number I, and this is going to be the index of number j. So, yeah. If the form is symmetric, I wrote this wrong, okay. Then we're going to have this guy. Therefore, we're going to have that A is symmetric as well. There you go, QED. So what we did basically was just show one side, which was way easier than the other. This side was like trivial almost, and this guy was slightly more difficult because we need to set them to specific things to actually show something. I don't think I actually showed this too well, but to be fair, I didn't understand the proof here either. But whatever, it is what it is. So yeah, if there's any questions, you can ask me. I'm probably going to be able to answer them. All right. No questions. Cheers. Great. Let us keep going then. Next part of the... This is gonna be terrible for you. Stucky, I'm terribly sorry. So, see what I wrote here. All right. So there's some tons of explanation about the following thing that I'm just going to say, but I'm probably just going to hand wave over it. But trust me, there's a good reason why I say this. We have A, right? That's gonna be our matrix for the form and everything. We also have B, which is the base of the vector space V. So A is going to be a matrix, right? That means that we can write it as A, I, J. This being like basically just saying it's a bunch of numbers, right? And this is the base of V. Now, what is the relation between these two? I am not terribly sure if I can explain this because I myself didn't quite get where it was coming from, but I also like kind of just understood it by osmosis, I guess. But A, if like we have that B is going to be equal to a set of vectors, a vector of vectors, which is basically just a matrix too. But it's going to be V1, V2, dot dot dot, Vn for an n dimensional basis. Then we're going to have that not this Aij is going to be equal to the product of Vi and Vj. I forgot the name of this. The form, yeah, the bilinear form of these two. So that's something odd to say, considering that we've seen absolutely nothing about this so far, but I believe that it is like wait, what? I think that's right. Yeah, it's pretty. So this is the definition actually. Now that I saw it, actually, Arden is just saying this is the definition. So I'm just gonna take it and run with it for now. I believe that's why I got so confused at first because he just kind of defined it and he said you can just define things, but he can if he explains it later, which is what he does. So Alex, what is the name of the book for this one? I need to catch up of the terms he's using. It's Algebra by Artin. Let me type it. There you go. There's a second edition which I have, but like we're using the first edition here because it's probably more widely available. I have no idea how, but I mean, considering that I found the other edition first, but whatever. So, okay. Now, for for we to tackle the next things, we kind of have to deal with base changes and everything. If you're, I don't know how much you guys have read on like base changes and stuff, which is basically just going from one represent no representation. How do I say this? Man, it's very hard to say what it is while using the concept itself, but it's almost like if you mapped every number to another number, basically. It's a little bit weirder than that, but it's a very important concept in math, in linear algebra. I am not sure, and Saki, can you like tell me if like they've seen base changes in the series, just so we're like doing this correctly?
Yes.
I'm
So
not
we
terribly sure.
originally we asked folks to come in with some like computational linear algebra experience. So and then in chapter 4 we saw a little more of that. So I think you're probably safe.
All right. So, okay, let's go with base changes then. So, we are going to have a base P. Not P, no, I'm getting ahead of myself. B is going to be the base of. Let's actually let me just zoom out and go somewhere else because this place is starting to get crowded. So let me go here. I think it will be fine. If we go a little bit to the side, there you go. Okay, so B is the base of a vector space V. So that's clear, I suppose. We're going to have then that B line is going to be to B times P. P is a base change matrix, which basically means that if we multiply these two matrices, we get a new base. A base has some requirements for it that I'm not going to really touch on, but essentially it makes it so that we can do a lot of cool things with, and basically just use it as the origin point for vector space V. Like it's a collection of vectors, but those vectors, they, as far as I can remember, they span V. So you can pretty much just say, oh yeah, I'm going to have 1, 0, and 0, 1. That's my basis. There you go. You have an entire infinite plane. Math. But it's all about fortunate basis, the base vector. next week. Alex, no worries. It's basically just like it's a collection of vectors that then, if you like do some cool math stuff with it, it becomes the vector space. Very useful things, and we're going to be working with it throughout the week. That's they're gonna follow, but like, yeah, and linearly independent vectors for n-dimensional space. Yep, that's been the space exactly. So yeah, that's right. That's what a basis is. There's a bunch of things that span the. A good thing to note is that there's a bunch of things that span a vector space, but only like a couple of them that span the vector space and are linear independent. They are usually very primitive-ish, and if you think about it, they kind of just describe the space itself. For example, if we have, let me go back to here, we have our squared, the basis of this guy is 1001. That's the identity matrix, right? But why is that? Well, because that means that if we have the vector 1001, we can linearly, like, we can do a linear combination of these two. Basically, multiply this guy right here by n and multiply this guy right here by m, sum them together, and we have any vector that is in here. That is what a basis is. And there's multiple bases for a single vector space. So much so there's a whole matrix that you multiply them to get another. It's called a base change matrix. It's very important to know that. So if you have any more questions, Alex and whoever else, you can tell me. I'm probably going to be able to tell you what that really means. So, next. Okay, there's a corollary here, which I have no idea where it really comes from. Oh, yeah, actually, it's not proven because it's a corollary. I forgot that. Kind of forgot that Artin does that sometimes. He just says, "Oh yeah, this leads from that. No explanation. Have fun." Uh, but that good book, even then. Okay, let me check where I can get this image that I used. It's 42 at the end. I think it's this one. Yeah. Right here, please. No, I can't throw it here. Damn it. Okay. Let's see what people are typing. Okay. Yeah, there's the standard basis of R2. Correct, Carly. It's just a like. This is the one we usually talk about because it's the default one that comes to everyone's base. But I did forget to say that is the standard basis and not the basis. There's, what's that, multiple that can do things. Whatever. Let's keep going. Where were we here? So another thing that you can think about is that if you have a vector x in V, if you multiply it by the matrix, by the base change matrix, just like the basis, while transposing, of course, you're going to have x line, which is a new vector that follows the basis that just got changed. You can basically do this to any vector in the vector space, and it just works. That also follows for this guy. Try to get to here. And there's also another thing that's very important that we have. This is how Artin writes it. It's a uppercase lambda. I really don't like writing as a uppercase lambda because it looks very good if you can write exactly like a computer, but it just looks like a triangle otherwise. Okay, So that is going to be equal to, that's going to be like the base, the form matrix in the base change. So what we're going to be doing, weirdly enough, is this. This is how you change the base of a form along with everything else. It's odd at first, but it works very nicely at the end, right? Let me see where this is coming from. What color is this? Oh, right. So, yeah, usually this is like how you define the base change for these guys. It just kind of follows from the previous stuff that we proved. He doesn't Artin doesn't provide a real like thing for it, but I suppose he wanted us to do it by ourselves. So I'm gonna let you do it by yourself if you want. But it usually works. Okay, what am I writing here? Why is I'm just oh sorry, punched my mic. But usually the God, I could swear my notes weren't this messy, but apparently they are. Oh my god. Okay. So A's. Okay. So there's another corollary that is, again, not really proven, but it's kind of just implied. It's something that you're probably going to be using forwards. Is that any let me see exactly how he says here, because it's very important to get the wording right. The matrices A, which represent a form equivalent to dot products. So basically, you're going to be like doing bilinear forms. The matrices A, which represent form equivalent to dot products or bilinear forms, are the matrices A equals P transpose P, where P is invertible. So that means that, wait, something else, my brain going fuzzy. Oh god, what am I doing? I'm having a stroke. P is invertible. So this basically means that any kind of like bilinear form matrix that you're going to have here is going to be in this form right here. Now, can we use this? Not too well, because as he says here, somewhere along the way, after stating this, it gives you a theoretical answer to the problem of determining bilinear forms equivalent to a dot product, but it's not very good because we can't decide what exactly can be written is as P transpose times P. Like, as far as we can tell, this is anything. So we didn't really answer anything here. We're just saying, oh yeah, bilinear forms, they exist. And we don't even have a practical method of finding P yet. So, you know, it's not a very satisfactory answer to begin with. That's why they're going to expand on it. Yeah. 1 second. Let me see if there's anything here. Let's go up next week, though. Goodbye, Alex. See you. He's already gone. Okay. Okay, it's probably here somewhere. Nope, I didn't even put it here. I didn't even say that something's positive, definite. Oh god. Okay, my notes are probably just very bad, but let's keep going. in order to represent a dot product, the matrix A must be symmetric. Positivity is also symmetric restriction. Matrix A must be that. Okay, so another thing that you have to worry about when you're doing dot product matrices is that you're going to be running into a lot of them that just aren't valid because x to the t a y, is that what he writes? No, x. He has x here too. Okay. Has to be bigger than 0. So, like, this guy has to be positive definite. Yeah. Where, of course, x is different to 0. Right? That's going to be a very strong restriction that we're going to be imposing upon this. One second. Let me. I don't remember exactly. Is the dot product itself positive? Hmm. I don't remember exactly. Let me search this up real quick. Oh my god, I probably broke the recording for a bit. Dot product positive definite. Yeah, the dot product is positive definite. So if we have the dot product of two vectors, it's always going to be of the same vector. I mean, like this. So this is going to be equal to xx. This is going to be bigger than 0 unless x is equal to 0, of course. Now, this is a very important thing to note because it's a very strong thing to help us define the rest of what exactly A can be as a matrix. So I'm going to be bringing up the next theorem, which is here. I need to screenshot this again, damn it. Go here, go here. There you go. So this theorem, the proof to it is extremely long. I have no idea if we have time. We have 10 minutes until the break, so I'm just going to be showing you the easy part and then we do the hard part after the break, I suppose. I'm not terribly sure when the break should start, but any moment now if you want.
We're not gonna like specifically time gate it, just when it's appropriate. So we could maybe do it now if you want to sort of keep all of this theorem together, or you could do what you said, do the easy parts and then come back for the hard part. Whatever feels
So
natural.
I think we're probably just then going to do it now because I do need to organize my notes a little bit, and also this theorem is absolutely immense. Like there is a whole like page here of proof. The first part, like if one implies two, very easy, just very easy. We already showed it actually because it's a corollary, and then if one implies three, it's a whole nother story. So we probably got to read up on that a little bit. So let's do a break now, if we can. I'm back.
Excellent. I didn't see
So,
any conversation in the chat, so feel free to get started.
all right. So, as we can see here, this is going to be a very important theorem. The following properties of a real n by n matrix A are equivalent. So these three are going to be saying the same thing basically. A represents a dot product with respect to some basis r to the n. So it's going to be like A is a dot product for is a matrix for some capacity of bilinear forms. 2, there is an invertible matrix P that does that form, right? That does this right here. So that P transpose times p is going to be equal to a. That was already shown specifically in, where is it now? There's a corollary that I probably couldn't drag in here, but oh yeah, it's because it's like right here. This thing right here, it's a corollary to, I think, the latest theorem that was proved. Actually, to a proposition, yeah, to proposition 1.9, I believe. That is a corollary. So one clearly is equivalent to 2. Now the problem is we have to show that 3 implies 1, or that 1 implies 3. I'm not terribly sure, but let me see what it says here. Oh yeah, and that 1 implies 3. Yeah, 1 implies 3 is already like shown too, because like if A is a dot product, it clearly is symmetric and positive definite. That's how like dot products are defined. So now we have to show that if A is symmetric and positive definite, it absolutely is a dot product, right? So how are we going to do that? We're going to be using the Gram-Schmidt procedure, which I'm not going to be explaining because it was already shown and it's absolutely immense in the book at least. So we're just going to be, the Gram-Schmidt procedure basically just finds an orthonormal basis. So what that means is that there's going to be a basis B, which is going to be normalized. So that means that each one of the vectors of B is going to be of length 1, exactly. And they are also a basis. And they are also orthogonal, which means that each one of the vectors, when you do a dot product with themselves, they're equal to 1. So that's a thing that like orthonormal bases do. First of all, they're a basis, of course. Second of all, they are normal. So each one of the vectors has length 1. And second and third, I mean, they're orthogonal, which means that this is true. Now, let's assume that we found that thing, right? We found the yeah, let's assume that we like found the orthonormal basis B or boy. It's going to be he's going to be used in the next bit of the theorem. So wait, theorem 1.22, I think that got skipped. No, it didn't. I'm just being very stupid. Okay, so no, yeah, I'm just being very stupid. Okay, for A to be symmetric but definite. I think that's right. Someone. All right, let me check real quick what this is saying. Where exactly the theorem goes from Gram-Schmidt to hey, that proves that. Let me see. Tells the base. In that case, theorem 122 tells us that there is a basis B line of Rn which is orthonormal. There is, because we just found it. It's a B that we have right here. With respect to the form xy equals that. So basically it has a form. But the basis will probably not be orthonormal with respect to the usual dot product of Rn. So basically that means that like if we have xt, a, y, that is going for like with vectors from this basis right here, with vectors from the vector space spanned by this basis, to be more specific, then you're going to have that these guys are going to be following like we're going to have a matrix A basically. We're going to have like a matrix A that has a dot product with these vectors that again are from a vector space that is spanned by B. Now, on the one hand, the matrix is orthogonal. Does if you now on one hand we have the like matrix A is going to be like the matrix A line actually. I'm not sure why I said this. Of the form that is going to be like no, it's just A. Never mind. A of the form that this thing is going to be equal to x, y. Did I do a parenthesis? So this matrix A, it's going to be satisfying the relation that if you get like, so you're gonna have like B, which is our new orthonormal basis, very cute, very nice, and then we're gonna have B line, his cousin, which isn't orthonormal, and it's the base that we started on. For B line, we're going to have A line, which is like this bit for B line. Yeah, it's gonna be A for B line, basically. So this guy, let me go down. There you go. If we have that P B line is going to be equal to B, then we're going to have that P T A P is going to be equal to A. That's just how we defined changing the basis of the matrix, of the dot product matrix up there. So, wait, where am I? So that clearly is the case. Now, since we have that, wait, someone asked a question, right? And I need to know about matrices. I thought you were falling off. My dog's on my chair here, it's just chilling. Okay, so now on the other hand, we have that like this guy right here. Since like B line, is it B line that we're talking about? Okay. Oh no. I wrote this completely differently. I'm sorry, ignore everything that I said so far. Thank you for people who are muzzlers. I fucking love people who are muzzlers. My god. I'm sorry for the expletive. Okay, let's delete all this. Now. Okay. B is going to be your... It's because like the notes are completely confusing on what like B line and B is meant to be. So sorry for the confusion, but like B is our orthonormal basis as before. B line is our not orthonormal basis. It was like before, right? It was before we changed. Oh my god, I think I deleted something that I shouldn't have. This line is staying. We're going to have that B line is going to be times P is going to be equal to B. So P is going to be a base change. And this guy right here is orthonormal. Orthonormal. I think that's how you write that. Anyway. Now B is orthonormal. That means that we're gonna have like a matrix A, which if we do like PT A line P is going to be equal to A. This guy is the dot product specific for the orthonormal basis, and that means that like there's something very important going on here. I think that's kind of right. Let me. What is exactly written here, man? Oh God. Now on the other hand, we have the matrix from X, Y, new basis. God, this is extremely confusing. I'm not sure where it's getting the like. It's just changing from between like being a line and not being a line, and I'm really boggling my mind about this. But basically, what it's saying is that tells us there's a basis B of Rn, which is orthogonal with respect of the form xy xt. So basically, there's gonna be like 8. This guy's correct. This guy is like the correct matrix for the form of for the form that is of the bases of the base that is orthogonal, and then it just talks about another one. That's weird. So basis b line. Oh, I see what it's saying. I think so. Let's ignore this last part. I'm terribly sorry for everything so far, but okay. So there is a, how should I say this? There is x and y from a basis of times past, which, it's b-line. It's b-line. This guy is going to be equal to xt a, let's call it a line, right? Why not? And y, this guy is going to, if this guy is like the matrix for the dot product of b-line, of the vector space that is spanned by b-line, then we're going to have another version of A, which is for the orthonormal basis, which is B. So we're going to have xt, A, not line, and this. This guy is going to be equal to pt, A line, P equal A. There we go. Right? Now here's the thing. Actually, I'm not sure. It's talking about like both of them being. Oh, I see. So, uh, with respect to this guy right here, like this basis is orthogonal to the basis of this guy, and then there's this guy right here, which is whatever. I am honestly almost given up on understanding what exactly Arden is trying to say here, because he's getting to a very important conclusion, but I'm not exactly sure what he's saying. My brain might just be fried at this point. I am sorry. Okay, let me see. Like, it's almost like he's changing the bases midway through the sentence. How to make sure from no. My God, 1 second. My dog is terribly sorry for that. My dog was bothering me. I hope no one opens that door. No. Okay. If you want, I can just give you the picture of what I mean. If someone can help you like understand what he's saying. But basically, he's saying this right here. So the fact that part 3 of the theorem implies false on the theorem, of course. For if A is a symmetric and positive definite, then the form defines it. Now, this is the part that I'm worried about. This. In this case, theorem tells us the basis is normal all the way to here. So, theorem 1.22, which is the one that we used basically it's the one that defines that, yeah, you can find an orthonormal basis. It's the Gram-Schmidt procedure, which is orthonormal with respect to the form xy equals xtay. By the way, the a and a line are like inverted, so there's that. Let me put a line on the ones that are meant to be that and the ones that aren't. Let me remove these. Actually, this is right. Yeah, I'm cooking. I'm bad at this. Damn. B line, A line, A line, A good. There you go. So, in that case, theorem 1.22 tells us there's a basis B of Rn which is orthonormal with respect to the form xy equals xta line y, but the basis will probably not be orthonormal with respect to the usual dot product of Rn. Like that basically just says that, like, yeah, there's like another basis which has its own dot product, but it's not going to be the usual one. Now, on the one hand, the matrix A line of the form xy with respect to the new basis probably should do this. The form xy with respect to the new basis B defines the relation P A line P equals A. So I'm not sure. Yeah, this is not working out, man. I'm so terribly sorry. Well, let me just say that, like, things here. Wait, what am I doing? The theorem is here. 3 implies 1. But, like, that's because when we, like, have this, I'm not sure where exactly, but, like, this guy right here is implied, actually, to be the identity matrix. So if this is the identity matrix, this is PTP, which then we can just if it's PTP, then basically just applies to the first one, which applies to the second one. So yeah, it works. But again, I'm not exactly stubborn about this, about proving this entirely. So exactly, Squirrely. Exactly. I'm sorry. Anyway. What's the next part? Okay, let's just jump to the next theorem, I guess. God. Now we have for a big one. This one, I didn't even get the chance to, like, prove, because the next section is I don't think I got to the part on the next section where we prove this one. Theorem 1.25. A real symmetric n by n matrix A is positive definite if and only if the determinant AI is positive for each I from 1 to n. For example, 2 by 2 matrix, this guy is positive definite only if A is bigger than 1 and this guy is bigger than, not bigger than 1, bigger than 0, and its determinant is bigger than 0, too. That's like very important for us because then we can just, this helps us define what exactly counts as a dot product matrix, because remember up here we had like we had to prove, okay, all we're trying to do is find what exactly counts as a dot product matrix. To be a dot product, you need to be positive definite and you need to be symmetric. So that's what we found here, that it's actually symmetric, right? That a bunch of these matrices are actually symmetric. And then we find here that, yeah, we can actually, determine if a matrix is positive definite by simply applying these two conditions to it, right? Now, actually, a single condition, yeah, it's just if the determinant is positive. But technically, it says two things here. I'm not sure why he separates one thing into two and then just has the first thing. Anyway, law of Artin. Okay. So from here on, my notes are even worse, honestly. They're just getting weirder. I'm not sure why. Not. Okay. 1 second. All right. So real metric and matrix. So this guy right here is very annoying to prove. So much so that we need a lot more context in order to actually get ahead to proving it. Now, there's some other things that I'd like to show you guys that are actually very important. Where exactly is this thing? What do you think about it? Oh god, this is the start of the second section. Okay, I have no idea why this is. Oh, that explains it. So, complicated guy. We need to find the next session, a bunch of work in the next session to actually like work with it and actually get around to proving this guy as Artin intends. Anyway, we're in the next section now. Let's start off with a very important proposition, which is that we suppose that symmetric form is not considered in terms of the of Okay, this one I'm going to try to prove myself with somehow from the actual. Wait, no, I don't want to share this. No. Damn Windows. Okay. Proposition. Suppose that the symmetric form, it's a symmetric form, basically. It's not identically zero. Remember that I said that we needed to like have symmetric things? Yeah, this is when we get to that. Then there is a vector v in the vector space, which is not self-orthogonal. Alright. What does that mean? That means that like we're always going to be able to find a vector that when you do a symmetric form with itself, and this guy isn't boring, then we get it to not be equal to 0, right? That's always going to be a thing, and I'm going to prove it right now. One second, where's that? Okay, here. My notes got confused for a second. Okay, so we're going to be saying first that this guy is not identically 0. There. Now, second thing we're going to be doing is that we're going to be thinking, what does that really mean? That means that, like, there's a pair of vectors that is different from 0. There's always going to be a pair of vectors in this thing that is going to not be exactly 0. Now, how are you going to get from two random vectors that not necessarily are equal to two equal vectors that are not necessarily 0? Well, let's just take the two vectors that we do know when they get formed, they aren't 0. So these guys, not 0. So let's take v and w as set vectors that we have, set names at least for vectors that we have. And, well, let's first check if v of v or w is different to 0, there you go. But if that's not the case, which is honestly probably going to be the situation for a lot of the time is not going to be the case. So we're going to be doing a contradiction now. Suppose that we have the v is equal to w, which equals 0. So these guys are just going to be equal to 0. Now we have that u, new vector that I just made up, very original, is v, no, 1 second, v plus w. There you go. Now, what are we going to be doing this guy? We're going to be expanding u bilinearly. This guy is going to be equal to v plus w. By the way, remember the operation is symmetric, so we can change these guys' places. Okay, 1 second. I thought someone was entering my room, so v plus w plus, let's start with this at least. It's going to be equal to, oh my god, what's happening to my mouse? Okay, get off you. W v plus w. Now we separate these guys too. So we're going to have v plus equal v w plus w v plus w. These two guys are equal, by the way, because, again, symmetric. So we go down here, and since we assume that like these two are 0, we're going to have 0 plus 2vw plus 0, which equals to, well, this can't equal 0, right? Because these two guys we saw right here up, that they are completely just and completely different to 0. That's just going to be the case. Actually, what? No. These two guys are going to be different to 0. So this guy, different to 0. So that means that u, not uw, uu is different to 0. There we go. We found our vector that we wanted to find all this time. That was self-orthogonal, aka u different to 0. There you go. Congratulations. We finished the theorem. Yes. No proofs left for the viewer this time. Anyway. Now, next proposition is going to be a little bit more complicated. We're going to have that... we're going to have a vector, w, which isn't the vector space, of course, because we're working in this space. And how do I say this? We're going to have that... First of all, w is different to 0, right? Because we can clearly find it here, so, you know, different proposition, everything, cool. Let me actually select a proposition here, just for posterity's sake. So I don't have to keep looking there, and that you guys can actually see it too. There you go. So, w is different to 0, and let's have big W, not very different, so that's why I'm going to do this, is actually going to be the span of W. So every single scalar times this guy that you can possibly think of, that's inside this guy right here, right? Then V is the direct sum of W and its orthogonal complement. Okay, that's cool, I guess. So what we're trying to say is that, like, usually if you take 2 dimensions, right? This is the xy plane. Congratulations, you've done something. Okay, so this is our span of... No, why am I doing this with 2 lines? This is the span of W, for example. It's just a big old line because it's basically just a point in each possible scalar that this can be at. That's how you define a line, by the way, in linear algebra. And then you're going to have its orthogonal complement, which is going to be this guy right here. It's going to be a 90-degree angle. And that means that... There you go. That means that there's going to be a W line, which is orthogonal to W. And what this thing is saying is that we have that the vector space that this originally came from is going to be the direct sum of these 2 guys. Oh my god, I'm centimeter. Okay. Now, what is the direct sum? The direct sum is actually pretty simple, especially considering they have sums already defined for us. So I'm not going to be talking too much about it, but it's basically just that if you have a set A with a direct sum to a set B, you're then going to get A that comes from A and little b that comes from little b. This is going to be like the form of things, and this guy is going to be... You're going to be summing everything. Wait, no, what am I doing? God, thank you. Okay, so there's going to be little a and little b. That's going to be the form of the things that are inside the set C. It's going to be a pair of these 2 guys. Now, what does the sum part of this mean? It means that you're going to be summing a, little a1 with little b1, and little a2 with little b2. So it's going to be a sum of everything in these 2 guys in this form. I think that's... this definition is correct. Someone can probably tell me if it isn't, but as far as I can tell, it is. What is happening in the chat, though? Damn. Alright, yeah. So this means that we're going to be getting a seemingly unrelated operation from two pretty much unrelated-ish sets and getting the entire vector space. If you look at this, it actually makes a little bit of sense because you're going to be like summon, like for example, if I sum this guy with this guy, it kind of just, if you just squint a little bit, this is a plane in itself, right? So the vectors are making a plane by themselves, which then with this, we're going to be doing a lot of, we're going to be basically remaking the vector space just in a different angle, but it doesn't really matter that it's a different angle because it's a vector space, it doesn't care about that thing. Brazil, Bass. Anyway. Let's see if I have anything saying about the proof of this guy. There you go. Here it is. Actually spans 2 pages. Wow. So we have 20 minutes. I think we can finish this one, and then I can probably leave, right? And Stucky can probably pick up from here, I think. And we'll have a grand old time on the next week, so... Okay. Let's begin by coming here, zooming out, seeing where exactly is free. We're making a good old tree here. Let's just go here. All right. So let me grab the screen cap. There you go. So there's a thing in the very early chapters that we have to show. That the like states that we have to show a couple things. So first of all, we have to have the like W does not intersect with its orthogonal, basically. That has to be like always the zero vector, and that is just true, like in general, because like the lines that I made down there, they're like here's the thing and here's the things. It's not exactly intersecting at zero, but that's just an error by me. Just I can draw exactly at the zero line, but it should be something like this instead. So they only intersect at the 0 point, and that's exactly what we want here. There's an intersection exactly at the 0 vector. Cool. Obvious enough, I suppose. Artin even says this is clear. The vector CW is not orthogonal to W unless C equals 0. There you go. Well, second of all, we have to show that W and the orthogonal of W span V. That is going to be a little bit worrying to prove, but it's going to be fine. So basically we're going to be showing that we have V, which is a vector in the vector space, and we're going to have that C times W, so a scalar times a times W is going to be equal to V if it's summing with like something with W line, and W line, god damn it, again. I hate the limitations of my drawing tablet, but W line is in here. So we have to show this thing right here, and we'll basically be golden. That's all we really need to do. Now, okay, so to show this, we solve the equation. Wait. Whatever. Let's go this. Okay, to begin, we're going to be solving what exactly? V minus AW, W. Okay, V minus AW, W is going to be equal to 0. And we have like that A is defined as is this A equals? Oh no, it's not. So yeah, no. First of all, we're going to be throwing this guy into a little bit of a loop. So instead of just equaling 0, I'm going to put the 0. Okay, and to be putting the 0 over here. And in the middle, we're going to be throwing some definition. So it's going to be basically just we're going to be separating this guy minus a w w. God, that definitely didn't make enough space. Whatever. W w is going to be equal to 0. So this guy is not going to be equal to 0. It's in fact different to 0. So we're going to have the solve for a here in this equation. Wait, where the hell is my... Oh, it's pen mode. Yeah, have to solve this equation. The solution to this is actually that A equals VW, WW. There you go. So if we have like A equals this, it clearly works. You can just do some basic algebra here. You can just pull this guy to the side and then pass this guy over. There you go. You have A. And that is very good because now we have... Wait, what exactly do I show this? And now we set... Actually, yeah, there you go. Now that we have A, basically we just have it, we're going to set V equals V. We're going to be setting V line, which actually W line up here, right? There's a W line up here. It's going to be equal to what again? Right, V minus AW. There you go. So what this is saying basically is that in order to like get this guy, you are going to be doing all of this, and then there you go. You have him, throw him up here. There you go. Yeah, then basically we just found W line, and therefore we found a vector which is in V. So that means that W and W orthogonal span V. There you go. Very good. Now that this is the case, that means that probably by the chapter 3, 6.4 and 6.5, which I do not have on hand right now, but it should be saying that this means that if you do the direct sum with the two guys, you are going to be getting V. So there you go. Now, there's a couple more concepts here, but I think we're running out of time, so I'm just going to be telling you one more thing. So there's a couple more concepts which we need to worry about, which is about a non-degenerate null space. I mean, a non-asymmetric form if for it to be non-degenerate. What does that mean? It means that like vector. It means that like the null space of it is 0, aka the kernel of it is 0. What do I mean by that? I mean that like if you have that VW equals 0, that implies that V and W are 0, right? That's basically what it's saying, because the kernel, after all, is everything that leads into 0, right? So if you have the kernel of this guy, if like there's nothing that does this besides V and W being the same number, then you're going to have that, okay, what numbers lead into the result being 0? 0. There you go. That's your kernel. Just a single number. That is it. Good. So the last conclusion is basically that like there's a like what I did so far, everything here is just the basic things that you have to know in order to start studying the bilinear forms. There's a lot more things that you're probably going to have to teach. There are the actual uses, the actual tools that are going to be developing. But like, for example, I spent 30 minutes defining a bilinear form. The rest of it was just saying, oh yeah, we can find a bilinear form, and it's a dot product. So like, this was like a bunch of the basics. So yeah, honestly, this is gonna be one of the more boring classes. And I myself, I haven't taught anyone before, and it's been a while since I read Artin, so I guess it was a little bit lackluster, but anyway, it worked, I think.